Cambridge University. Boat race partaking. Earth science taking. And offer making. But how do we answer their most difficult questions? Let's take a look. So our first question of the day is, what is your favourite element and why? So this is very subjective, but I'm going to tell you my favourite element is gold. As for the reason, well, gold is one of the oldest elements on our periodic table, and it's one of the most expensive per 100 grams. It has an extremely low resistivity and is very resistant to oxidation. It is highly conducting, making it useful in computing and electronics, and its radioactive isotopes make it also ideal for medicine, as both undergo beta minus decay and have very relatively short half-lives. It also has great potential in biochem, as its radiation is less energetic than radium, and when used as a contrast agent, it does not have to be injected multiple times, as the body doesn't see it as toxic and feel the need to push it out. Also, while doing research for this, I discovered that it is used to create the colour red in stained glass windows. And who doesn't love stained glass windows? Next question is, why are transition metals so colourful? So to answer this question, we need to understand how colour works. So white light is made up of many different colours or wavelengths, each of which have their own energy. And all of these wavelengths are absorbed by the object, except for the one that represents the colour of that object, which is reflected, and so you view it as that colour. So my red object here has absorbed all other wavelengths except for red, which is reflected into the eyeball, so you would see the object as red. Now it's important to know why it's reflected. A specific wavelength of light will excite the electrons, causing them to move to a higher energy shell. And then when they move back down to their original energy level, they will release that wavelength back out. So then what's special about transition metals and their electrons? Well, they're all in the D part of the periodic table. That's where the transition metal block is. So all your electrons, or valence electrons I should say, will be in a D orbital. Also, metallic bonding may have something to do with it, because obviously you have charged positive ions amongst a sea of delocalized electrons. In this giant structure, you'll have an average energy that electrons occupy, and obviously you'll have higher and you'll have lower than that, because that's how averages work. And when light enters, an electron moves shells, it emits that red light back out, which gives you the colour of the transition metal. Next question is, how many isomers of C4H8 can you draw? First of all, we need to note that C4H8 has a value of 1 dBe, so 1 double bond equivalent. So it can either have a double bond or it can have a ring. So going down the double bond route first, you can have butyne or you can have butyne. Then with butyne, because the bond's in the middle, it displays EZ isomers. So at the moment we've got 3. So then comes the ring side, and obviously you've got cyclobutane, but you've also got methyl cyclopropane. That's 5, and then I ran out of space, so I had to do it on the next photo, but you've also got methyl propene. So how many can I draw? The answer is 6. And I hope you enjoyed that little break, because now we're going back to transition metals. Why are transition metals good catalysts? And again, I'm going to refer you to the fact that they all have partially filled d orbitals because they're in the D block of the periodic table, which means that almost all of them have multiple oxidation states, which help them to form intermediates, which helps them be catalysts. But there's also other reasons. So here I've written out the oxidation states and ions of cobalt, and just here is what we would call a complex of cobalt. And in this photo here, ammonia is acting as something called a ligand. And each of these nitrogens can activate the cobalt, which allow it to act as an even better catalyst by creating a shorter activation pathway. Next one's a relatively easy one. How many moles of water are in this bottle? We're going to assume a standard 500 milliliter water bottle, which is 500 centimeters cubed. And the density of water is 1 gram per centimeters cubed. So in all, we have 500 grams of water. See what I mean? Really not that difficult. So we're going to put it into this equation that we've done forever, and we're going to get about 27 moles of water. And that's it. That's the question over. The answer is 27.8 moles of water in a standard 500 milliliter bottle. Next one's a little bit more difficult and a little bit more random, if I'm being honest. What is the density of air in this room? What about outside? And what about Beijing? So at room temperature pressure, 24 decimeters cubed is equal to 1 mole of gas. And of that 1 mole, we're going to assume 0.8 is nitrogen and 0.2 is oxygen. I'm going to assume everything else is negligible. So density is measured in meters cubed. So to get from decimeters cubed to 1 meters cubed, we're going to times by 41.7. And so we're going to have to do the same with the number of moles as well. We're going to apply the 80% 20% ratio, and we're going to end up with 33.36 moles of nitrogen and the rest oxygen. And we're going to do this equation again. So the relative atomic mass of a molecule of nitrogen is 28 and of oxygen it's 32. We're going to put in our mole values that we just calculated, and we're going to get that the mass of nitrogen is 934 grams and the mass of oxygen is 266 grams. Gives us 1,200 grams total per meter cubed, or 1.2 kilograms per meters cubed. So what about outside? Well, if we assume room temperature is 25 degrees, at the moment outside it is a lovely chill 4 degrees. We're going to work out the new volume 1 mole would occupy at 4 degrees Celsius. So we're going to use PVNRT, we're going to sub in our values, and pressure we're going to assume is still 1 atmosphere. It might be slightly less because it's colder, but really not noticeably. We're going to get 23 decimeters cubed as our answer, and then we have to feed it back in. So by now we've done this equation about 5 times. You get these answers. You get 28.8 times 10 to the minus 3 kilograms. You then divide that by your volume, work out the density at 4 degrees Celsius, and your answer is about 1.25, so it's denser at 4 degrees. Now I'll admit the Beijing part of this threw me a little bit, but large data set from maths helped me out. So we can assume because Beijing is closer to the equator, it's going to be warmer and so less dense. And so we can assume that it'll be about 120 because it's not 21 degrees warmer in Beijing than it is in the UK. We can assume that density in Beijing is about equal to the density at room pressure in the UK. So next question is, what's the difference between enthalpy and entropy? Now we went over entropy briefly in my last video, so I'm going to say go watch part 1 if you haven't already. First off, obviously we have the units. Enthalpy is measured in joules per mole, entropy is measured in joules per Kelvin. Enthalpy is a measure of how much energy is required to break bonds, whereas entropy is a measure of order versus disorder. When calculating enthalpy, you need standard conditions, 25 degrees Celsius, 100 kilopascals, whereas to calculate entropy, you don't need anything. Now, enthalpy can be positive or negative, whereas entropy is always positive in spontaneous reactions. And spontaneity is a really difficult thing to define, but a really good analogy I found online is you have to push a boulder uphill, but at the top you can just let it roll down by itself. And likewise, things will go from order to disorder by itself, but you have to put effort in to make them go from ordered to disordered. So, next question is, how do glow sticks work? So, I wrote down 3 criteria. Glow sticks have to be luminescent, so they have to glow, obviously. They have to snap to work, because that's how you make glow sticks work. And the reaction has to be reversible if the glow stick is frozen. So for the snap part of it, I imagine it's 2 capsules inside of each other, one made of a weaker material, or more brittle should I say, and one made of a stronger material, each holding a different reactant. A forward reaction would have to be exothermic, although not enough to hurt anyone because you don't want to come out of a rave looking like Two-Face. As for the chemicals involved, the product would have to be luminescent, it would have to glow. Would also have to be non-toxic, just in case you break it, you don't want to breathe in dangerous fumes. And then obviously it would have to be coloured, and that will probably be a dye, but it could just be the reactants. And when I did my research afterwards, I found out that the thing inside the glass tube is H2O2, and then there's a complex organic compound on the inside. Next question is, why does food taste better hot? And there's two things to consider: is it's either the food or it's your tongue or taste buds, or it can be a mixture of two. We know when we look at heat, particles vibrate more when they're heated. So maybe it's the case that particles at a higher temperature collide with your taste buds more and so give off a better taste or more strong taste. And when experimentation was carried out, it was noted that caffeine tasted more bitter and sucrose tasted sweeter when it was heated. However, it was noted that salt didn't taste any saltier and citric acid didn't taste any more sour. So that really takes away from our food argument. So then we have to look at the tongue. What I've drawn here is where your taste buds are for caffeine and for sucrose. Your sweet taste buds are towards the front of your tongue and your bitter taste buds are at the back of your tongue. It may be the case that, like enzymes, taste buds only work well or better at certain temperatures, and that would also make sense that your sour and your salty taste buds don't work better with an increased temperature because maybe they have a wider range. And also your tongue has receptors on it that may react differently to texture under different temperatures. So why do we use water to dilute solutions? Well, there are a number of reasons. For one, it's a solvent. It's also polar, it's liquid up to 100 degrees, and it's non-flammable, which makes it all very useful. It's cheap and it's abundant. Even distilled water is cheap. It's universal. Water dissolves the most molecules than anything else. Also an international standard. If everyone uses it, then everyone knows what everyone else is doing. And finally, it's pH 7, so it's not going to affect the pH of whatever you're diluting. Compare and contrast hydrochloric and phosphoric acid. So similarities, they're both colourless liquids, they're both acids obviously, and they're both relatively strong. That is stronger than something like ethanoic acid. Differences, there are a lot more. Hydrochloric acid is monoprotic, i.e. it contains one hydrogen, whereas phosphoric is triprotic, it contains 3. Phosphoric acid doesn't contain oxygen, whereas phosphoric acid does, and if you don't know what this does, I can highly recommend Acids and Alkalis Part 2, I think it's in. God, I am just shilling all of my videos. And hydrochloric acid is a binary acid as it only contains one other element other than hydrogen. The general rule, if they're the same concentration, hydrochloric acid will have a higher Ka than phosphoric acid. And that's partially because hydrochloric acid dissociates fully, whereas phosphoric doesn't. So why is vanadium so special? So vanadium is a transition metal. This is its atomic mass and atomic number. And then because it's a transition metal, it is in period 4, group 5 of the periodic table, and that puts it in the D block, which we spoke about earlier. It has one isotope, which is vanadium-50, which has a massive half-life. It's used a lot in alloys because it's corrosion resistant and it's very tough, so it's used in things like armoured plating, and its low neutron absorption means it's really useful for fusion and fission reactors. This one's a bit of a subjective one. Where does chemistry end and physics begin? So I've drawn it out in a Venn diagram, and we'll have a look at this. So in my chemistry part, I've put enthalpy, acids, synthesis, and polymers, and that's just a few. In this intersection, I've got materials, nuclear, gas laws, and quantum. And then just for physics, I've got motion, kinematics, space, and electricity. So my answer to the question is basically, when you reach the end of the last atom of your compound, then it becomes physics. When you start analysing what happens when you throw it, or when it orbits another thing, it becomes physics. And only physics, no chemistry involved. So, last question of the day. Can you change an exothermic reaction into an endothermic one? So we need to compare exothermic and endothermic reactions to answer this question. So in an exothermic reaction, more bonds are made than are broken because energy is released when bonds are made. Here we have a simple exothermic reaction, it's just the combustion of ethanol. The enthalpy is negative, and you can see why because of how many bonds you need to break versus how many you need to make. So if we pretend that this reaction is reversible, it's not, but let's pretend that it is, then you can see that that would be endothermic. So, in short, the answer is no, because if you reverse the reaction, you're changing the reactants, and it's not the same reaction. And again, I'm sure you could make CO2 and H2O from an endothermic reaction, but that's not the same reaction, so the answer is no. So that's going to be it for today, guys. I really hope you enjoyed. Feel free to check out part 1 if you haven't already, or watch it again if you have. Please like and subscribe, and feel free to join me next week when we'll be talking about liquid crystals. I hope to see you then. Bye.